Alright, basically we need to write two different equations and then solve for the time in each one and compare, and that's all this is. I'm going to use M and P to keep these guys straight. For Michael, he invested $1,000 and earned 4.7% annual. What's his equation look like?
1,000 E 0.475.
It has to have a 0, 475. T, okay? And we're setting that equal to 1,800. We're trying to figure out when it will get to $1,800. Okay, P for Peter, 1,200, same, mostly the same, everything else except for different rate. Also trying to get to $1,800. How do we solve for T in these? So this was, the part we just wrote was review of previous to the testing week. Now we're talking about how do we solve for T, that's review of Friday. So what's our goal? Like, be very specific, what's our goal? Get T by itself, yeah. And so then you said something about log form, right? Okay? Yes?
Is Peter's supposed to be 0.25 or?
Oh, yes. It is indeed supposed to be different. Thank you. Okay. First, we wrote in our notes, get the exponential by itself. So we need to divide off both of these. And what's this one? Let's do e to the 0.0425t equals 1.5. Okay. How do we undo e to the power of? That's the next step. How do you undo an exponential? You have to take the log of the same base, right? Mm-hmm. So what's the log of the same base as e to the power? That's natural log. So we're going to natural log both sides. And then we're just left with kind of a usual or regular function or a equation. On this one, I'm going to move it up over here. So on this side, we'll get 0.0475t. And then natural log of 1.8, that's what power of e gives 1.8. That's what that is actually asking. So that's 0.5878. So again, just a number, natural log of 1.8. I forgot the t. How do we get t by itself at that point? Just, it says 0.0475 times t, so we just divide it off. And we'll get t and some number. If you're keeping all this in your calculator, it's easy enough to just hit divided by and not have to worry about retyping that number in. So about 12.4. What is the unit of 12.4? What should we label it? 12.4 of what? Here, I'll scroll up. It's years, yep. So it took roughly 12 and a half years to get that extra $800. All right, next one. Again, it's the same solving process, just slightly different numbers. Natural log of 1.5 is a little bit smaller. So 0.4055. Okay, and then just divide off 0.0425. And we get 9.5. So in this case, was it better to have a higher interest rate or a bigger down, like initial investment? Yeah, so think about that. We did that problem a couple weeks ago where we calculated how you could be potentially millionaires by the time you retire with a pretty reasonable plan. But this kind of goes to show that getting a good solid initial investment is pretty important, right? It can help a lot. Any questions on this one? It's basically doing the same thing twice. So if you have one of these, then you should be able to get both. Because only the numbers change, not the process. I think at this point, I would expect you to be able to do this pretty smoothly. If that's not you, you need to probably ask me for help or do your homework or address something. Because these are pretty easy ones, honestly, for solving. They're pretty much a few easy steps. Where we're headed, it gets a little more complicated. It's not horrible, but it is definitely more than this. And that will kind of be how we end the units. Probably sometime next week we'll be ready to test. Just giving you kind of a heads up as to when to be prepared for that. Okay? Let's check your homework answers, and then I have a couple things to show you today. Hopefully we'll get to them. Most of these answers are pretty quick to say, and I can do a couple of them if you need to at the end. So number 23, you should have rewritten as log base 3 of 6,561 equals 8. Guys, remember on these first problems, 23, 5, 7, and 9, it's just rearranging the numbers, okay? 25 is log base 5 of 1 equals 0. 27, 10 to the negative 2 equals 1/100th. And 29, e to the 5th is approximately 148.41. How'd those go? That conversion is really kind of establishing your understanding of what a log looks like and means. So it's important to get that really solid. 31, should have got negative 3. 33 is 4. 35 is 3. 37 is undefined, meaning I cannot put an exponent on 7 and get 0. That doesn't work. Any questions on those 4? All right. 45 is 142. 46, 2.6417. If you didn't round to the 10,000th, but you got the other numbers right, then don't worry about it. The process is correct, right? 47 is 2.7964. 48.6990. 49, 2.8904. 50 is 3.1. 51 is about 22 years, which that problem is basically the same as what we just did on our warm-up. So, how'd those go? Are there any that you'd like to do? Okay, awesome. Keep that in mind. I did remember in our notes we called it basic solving, and we're going to extend that, but this still comes up, so keep that kind of fresh. But right now, grab your notes. We're going to move on to some graphs of logarithmic functions. And maybe if we have time, we'll talk about inverse functions as well. Have you guys ever done inverse functions before? Like finding inverse? Does it sound familiar? That's okay. All right, quick review. What does the exponential graph look like? So let's just do 2 to the x. You guys remember? Oh, I'm glad you're looking up there. Good job. Yeah, a lot of people are just kind of doing the basic shape. So we know it never crosses the x-axis, so that means its output values Never will be 0 or negative. Guys, what do we call the output values? We have a name for it. We've been analyzing almost every chapter this year. Starts with an R. The range. Or the what?
The range.
The range, yeah. Is that what you said?
Yeah.
Good job. Okay, so keep in mind on the exponential, we have a restricted range. What is the range for that? Without transformations. Like we're not shifting this around, just the plain old.
Oh, negative.
Well, where does it start with? Remember, on a range, we go from bottom up. No, it doesn't.
Zero.
0. Yeah. Okay, so when I say it's restricted, it's because it starts at 0. That side of our interval is not infinite. Okay? So it's not putting out anything negative or 0. Are we clear on that? The reason I want you to be clear is because the log function is just the inverse of this one. So what's going to be restricted on it? Okay, let me graph it for you and see if you can tell me that. Because when you do an inverse, it reflects across the line, this line, y equals x. So where should this green line go to be reflected across that line? It looks like that. Okay, so that's our log base 2 of x. That's that function. So when I say something's restricted about it, what is it? True. Yes, the y can equal 0. Y can. That would be this point right here. So what? You're on the right track though. X will never be 0. So in terms of domain and range, what are we restricting now? Can I input all values I want to this? No. So what do we call that? The set of input values is called what? It's called the, it starts with a D. The domain, okay? What's the domain for this one? No, it's 0. It can't be over here in the negatives, right? Yeah, so do you see how for our exponential, the range was restricted 0 to infinity, but for logarithmic, the domain is restricted. That's a property of inverse functions. Okay? They're both always growing, but in different ways. Okay? How would you describe the rate of growth in a log function? Is it getting bigger or smaller? The rate of growth. So is it growing faster here or faster here? Faster down here. It's way steeper, right? So our rate of change here is really steep, and then it starts flattening out quite a bit, actually. Whereas that was also inverse on our exponential. It started off with a slow rate of change, and then it jumps up to a high rate of change. Everything about it is the opposite, if you want to think of it that way. Okay? Inverse, undo, opposite, those words all kind of go together. Okay, here's the official look at them. It doesn't, sometimes students think that this is going to flatten out up here, but it doesn't. Okay, it keeps going, it keeps getting bigger, it just doesn't do it very quickly. So let's talk asymptotes. I'm going to leave this up here. What's the asymptote for the orange graph, which is exponential? In fact, I should probably put that up here. Y equals 2 to the x. What is the asymptote for it? Y equals 0. It's the horizontal asymptote, right? Is the x-axis. So that's another thing that changes, because what kind of asymptote do we have for the log graph? Now it's a vertical asymptote. over here, it's the y-axis, right? You guys remember all your asymptote stuff from the last chapter? X equals 0. Remember, for a vertical line, it's x equals, not y equals. Right? So, speaking of graphing in terms of both of these, what changed this horizontal asymptote and made it either shift up or down? You remember, in terms of A, H, or K? Can you give me a function rule that would shift the horizontal asymptote to 2? Well, let's do 1 so I can graph it. Y equals what? 2 to the x is our parent graph. How do we shift that horizontal asymptote up?
Plus 2?
Yeah, so plus 2 at the end, that raised the horizontal asymptote, correct? How do you think we shift the vertical asymptote to 2? Let's say I want it over here at positive 2.
Equals.
Okay, over here. Say it again, sorry.
2x minus 2.
Like this? Yeah, you got it. You did. Good job. So basically all you're thinking of is how did we shift it left and right? Well, that was H, not K, right? So now that would take this normally on the y-axis vertical asymptote and shift it over here. So now our graph would look like that. Same shape, like we didn't mess with that at all, but it shifts it to the right because of that x minus 2. So new, this time vertical asymptote at x equals 2. So do you see how pretty much everything is different about these two graphs? Domain's different, range is different. How we draw the asymptotes is different. Which letter changes the asymptote is different. How they grow is different. And all in a very specific way. It's like the exact opposite. Okay? Let's go put some of this down and then we'll start looking at some of the different versions of the graphs. Yeah, we'll get there faster. We'll start with just sketching the graph. It has an x-intercept, no y-intercept. That x-intercept is at 1. Okay? It has a now domain restriction. So it has a vertical asymptote where? I'll start off, x equals what? Like for the parent, it's x equals 0, but if we want to generalize, what will it be? What letter should go on the other side of that? Well, that's a number. For this one. But for the, like for any case, like the one that Lily just told us, hey, it shifts at 2, x, y, the 2 to the x minus 2.
Oh.
Remember x equals h, right? X, the h is going to tell us where that horizontal shift is, which tells us where the vertical asymptote is. Because it probably would be a good idea to start studying your notes again from the stuff prior to this. I can tell you're a little shaky on the exponential graphs, and you don't want to be lost on that for your test. Okay, the transformed version of this, we'll just write kind of the usual a log base b, so this applies to all logs, of x minus h and then plus k. All those things do the usual. It's just that our asymptote now is defined by h instead of k. But otherwise they change the graph in the usual ways. And if you want to rewrite that in this section, I'll let you look it up in your other notes. But I think this is the 4th or 5th time we've seen what they do. I suppose it'd probably be prudent to put I equals log base b of x. Okay, well, let's just quickly say what these do since it's been a couple weeks. What does A do to, or any of our graphs? What does A do? I think you're about to say it.
Stretches or compresses.
Yeah. Okay. Like if A is 10, what's this going to look like versus the one I drew? Is 10 a stretch or a compression? It's a stretch, so it would shoot up faster. Okay. If A is 0.5, what would it do to this one I drew? Yeah, it would squish it down more, and I'll show you this in a second. Okay, and when we already saw, Lily told us if h was -2, it moved it 2 to the right. What if we want to go the other way? Plus 2. And then k, of course, moves it up and down. Okay, so a couple of quick illustrations of that. Here's natural log, just the regular red natural log one. If you're using Desmos, by the way, so let's say I want to shift this around. The log ones are in the functions menu, so you have to click over here, scroll down a ways. Unfortunately, I feel like those should be more accessible, but it's kind of buried in there. All right, so let's just get log of x in here, and then we'll change. So if I do that 10 out front, look how much stretched it is compared to the red one, which is original. It's shooting way up before it heads off to the right. Okay, so to zoom in or out and show you. It's quite different. Okay. And then if we put a 0.5 there, you said it should compress it. So that's not quite as stark of a change, but it definitely squished it down, right? And then let's just kind of do all the changes. I'll leave the 0.5 in there. If I do -1, where's this going to go? Okay, so -1 just moves it to the right a little, and then again, if we do like +3, +2, it just moves it up. Okay, so pretty usual, right? Do you agree with that? Okay. Now we also have the fact that with this we can change the base as well. So like natural log or log base e would be different than log base 5 or log base 25. It's going to look different. In fact, I'll put that up here just to illustrate. Let's do like log. Where are they? There they are. What shall we do? Log base 5. How about that? Okay, so the black one, see how it's squished down a little bit more? So it's kind of functions like A. Cool. All right, I want just grab some kind of blank scratch paper. You're not turning this in or anything, but I just want you to work through some of these with me. I think this will go pretty quickly. Just somewhere where you can draw a few graphs. And we're going to do it pretty sketchy. Like, it's not going to be official much at all. As usual, I think sometimes it helps to draw the parent function and then transform that, but if you feel comfortable doing just the transform graph, you're fine. I don't care. So I'm going to give you like 10 seconds each to sketch these, maybe 15, okay? So think about what your parent function looks like and then what these two will do. And again, it's just a sketch, just make it a relative graph, not a perfectly graphed graph. Okay, so this is natural log of x. What does the plus 4 do? Shifts it up 4. Okay. This is a very vertically oriented graph, so how do you show it being shifted up 4? Nope, that would be this. Yeah, so guys, the 4 has to be inside of the natural log to shift it left or right. And so you'll have parentheses around it in that case. If there are no parentheses, then the 4 is stuck at the end and it's k. So it just shifts it up. Yeah, I'm glad you brought that up because it is important to show these clearly with parentheses when you're writing them too. So how do you show this shifted up? Since obviously this tail is not really going to change, it's still going to approach the y-axis like that. Well, that is normally at 1. Will that shift right or left when I shift this whole thing up? Yeah, so my new one kind of needs to go like that, right? It's mostly, it's hard to tell a vertical translation with these. Here, let's put it on Desmos to make it official. Natural log, there's that one. Plus 4 at the end. Okay, it just kind of moved up. Same shape though. Okay, how about 5 out front? What does it do? Yeah, so it's going to do something like higher up like that. Okay, how'd you do on those? Everybody good? Okay. Yeah, I figured this would go pretty smoothly. Let's do these two. This time I do want you to talk about the asymptote and x-intercept. It says, how do they compare? I think you're probably able to give me the equation of the asymptote and then just tell me how the x-intercept changes. So maybe 30 to 40. Yeah, that was the parent. Okay. So in terms of this one, what does the negative do out front? Yeah, so it's going to do that kind of thing. Okay, but it's also going to move around. Where does this minus 2 or x minus 2 move it? Which way? Right. To the right, good. Okay, so our new vertical asymptote is on x equals 2. What does the plus 3 do?
Up 3.
It does move it up 3, and so something like that for your graph. New vertical asymptote was at x equals 2. How'd that one go? Mid. Okay.
Yeah.
How about this next one? Okay, good. Our new vertical asymptote is at -1. And then a shift up one is not super different from what we have here. Something maybe like that. How'd that one go? Okay. Notice, I didn't say this, so I want to go back and point it out. So on the parent function, natural log or log base something of x, notice we don't have a y-intercept. So if you plug 0 in there, it will say undefined, okay? But we do now have an x-intercept instead. So something to keep an eye out for.